Hello everyone, welcome to my talk entitled Dynamic Splitting Method for Rare Events Simulation. This talk is part of a mini-symposium that we have organized in MCQMC 2020. During my presentation, I will follow this outline. I will start with the small introduction to briefly motivate the problem. In the second part, I will present the proposed multi-level splitting algorithm. In order to emphasize the wide scope of applicability of the proposed approach, I will present in part 3 4 different applications related to the performance analysis of wireless communication systems. In part 4, 2 heuristics that enable the selection of levels that will be used in the multi-level splitting are presented, and before concluding, some selected simulation results will be shown. Sums of random variables are often encountered in various applications, such as in the performance analysis of wireless communication systems. For example, the computation of outage probability at some receivers like MRC, EGC, or GSC receivers turns out to be equivalent to the computation of the CDF of independent random variables. The second application is in the computation of the outage probability in the presence of noise and interferences. Another application where the sum of random variables is encountered is related to the computation of probability of misdetection of pointing and alignment of free space optical communication systems. These 3 applications and many others can be grouped into a single framework, which is the computation of the probability that a quasi-monotone functional falls below a given threshold. The classical splitting cannot be applied to an estimation problem with time-independent distribution. In fact, in its original form, the multi-level splitting algorithm involves a continuous time Markov process whose paths are split in an attempt to help the process enter a small set of interest. Hence, the idea that we adopt here is to embed the time-independent distribution of interest within a continuous time Markov process. This Markov process has exactly the target distribution at a specified time instant, and with this embedding, we apply any suitable version of the dynamic splitting algorithm to estimate various metrics related to the performance analysis of wireless communication systems. 2 main contributions of the proposed approach are emphasized in this talk. The first is the unified aspect. So the unified aspect that our algorithm have is the fact that we do not assume any particular class of distributions of the random variable into consideration. The second contribution is the wide scope of applicability of this approach by emphasizing in this talk that we can apply our algorithm to various applications related to the performance analysis of wireless communication systems. Let's talk about the algorithm now. Recall that the aim is to estimate a rare event probability of the form as in equation 1, where L is the probability that a functional S of X is less than a given threshold gamma. X here is a random vector of independent random variables with CDF Fi. By dividing the index set 1 to n into 2 sets I and D, the importance function S is said to be a quasi-monotone function if xi less than yi for all I in I, and xi bigger than yi for all I in the index set D. This implies that S of x is less than S of y. An example of a quasi-monotone function is S of x equal to x1 plus x2 plus xn. It is clear that this function satisfies the quasi-monotonicity property with the index set I equal to 1 to n. Recall here, as we have mentioned before, that there is no underlying Markov process that we can split here, and hence the original splitting algorithm cannot be directly applied to estimate 1. Motivated by this, we choose to embed the density of x within a continuous time Markov process x of t in such a way that x of at time 1, the process at time 1, had the same distribution as the random vector x. And given this embedding, we apply the original splitting idea to estimate the problem 1. A suitable Markov process for our purposes is the multivariate gamma process. Let me first recall what is a gamma process. It is a process that starts at 0 at time t equals 0. It is continuous time and continuous state space process. It satisfies the continuous, it satisfies that the increments are stationary and gamma distributed. The increments are independent, and the third definition, or the third property, is to ensure that the sample paths of the stochastic process J are almost surely right continuous with left limits. Also, we recall the definition of a multivariate gamma process. So let Gi from I equal 1 to n be n independent gamma processes. Then the collection of this Gi construct what we call the multivariate gamma process. Next, in equation 2, we construct the process, the Markov process x of t, and we clearly observe from this equation that we have almost sure partial, and in fact, in this case, total ordering of the vector for all s and t positive. This means that when I is in the set I, xi is increasing in time, and when I is in the set D, xi is decreasing in time. Also, we observe that at time t equal 1, each xi at time 1 has the desired distribution fi. This means that the outcome of the original vector x is just a snapshot of the state of the Markov process at time t equal 1. Another observation is that s of x of t is an increasing function of time, and hence the largest time such that s of x of t is less than gamma exists and is unique. Also, if we consider an interval or a partition of the interval 0, 1, then the state space can be decomposed into the decreasing sequence of events as in equation 5. Next, we write the quantity of interest L to be the product from L equal 1 to capital L of some conditional probabilities. This decomposition now suggests that given T1 to TL, we may estimate the conditional probabilities sequentially, just as in the classical splitting algorithm. For more details, the steps of our algorithm are summarized as follows. We start by simulating S number of independent versions of X at time T1 and collect all the states that satisfy S of X at T1 is less than gamma. Then we randomly select or we randomly resample S Markov states from the set chi1, and each Markov state evolves for an extra t2 minus t1 period of time. Then we collect all the states for which S at S of x at t2 are less than gamma, and we save the states in the set chi2. Then we repeat this process until the final time TL, and then take the product of all the conditional probability estimates to obtain the multi-level splitting estimator in equation 7. Here is a small illustration of the algorithm. S is equal to 2 here, the number of level is 3. We observe that the path, the trajectory are all increasing in time, and since only one trajectory survives at time t equal to 1, then we conclude that the estimate in our case is equal to 1/8. Let us move now to the applications. The first application is the CDF of the sum of independent random variables. This serves to compute outage probability values at the output of some diversity receivers related to the performance evaluation of wireless communication systems. In this case, S of x is equal to the sum from I equal 1 to n of xi, and the random variables x1 to xn are independent and represents some fading channel amplitude and some fading channel gains depending on the diversity algorithm that we are using. Note that in most of the cases, the CDF of the sum of independent random variables is not known in a closed form expression. This is the case for the log normal, the Rayleigh, Nakagami, Rice, and etc. These are examples of distributions that are widely used in the context of wireless systems. The calculation of L has been extensively investigated in the literature through either approximation methods or efficient simulation techniques. The multi-level splitting algorithm, as we have said before, have this unified aspects compared to the existing estimators. It is applicable independently of the distribution of x1 to xn. It is also important to mention here that our algorithm can be easily applied to many classes of dependent random variables. First example, it can be applied to any Gaussian copula model as long as the square root matrix C of the correlation matrix sigma satisfies that Cij is positive for all ij. In this case, if S of x is quasi-monotone, then we can easily prove that S of C of x of C times x is quasi-monotone. Another example is in the transformation 8. We may prove that this transformation preserves the quasi-monotonicity as well. The second application is related to the evaluation of outage probability values in the presence of interferences and noise. In fact, the aim is to estimate the probability that the ratio between x1, which represents the received power of the useful signal, and the sum from I equal 2 to n of xi plus eta, where x2 to xn are the received powers of the n-1 interfering sources. Eta is the variance of the additive wide Gaussian noise. And here we assume that x1, x2, up to xn are independent and non-negative. A close look into the literature reveals that constructing a simple generic estimator that works for a wide range of distribution is of practical interest. The problem 9 fits our multi-level splitting framework since S of x, which is given in 10 here, is quasi-monotone by choosing I to be the index set 1 and D to be the index set from 2 to n. The third application corresponds to the partial sum of ordered random variable, which is given in equation 11. N bar here could be any value from 1 to n. X1 is the maximum, X2 is the second maximum, etc. X1, X2 to Xn bar represent the best n bar out of n ordered fading channel amplitude or fading channel gains depending on the diversity receiver that we are working with. This problem has been tackled by few studies in the literature, and given that S of x, which is given in this case by the partial sum of xi from 1 to n bar, satisfy the quasi-monotonicity, then the application of the multi-level splitting in this case is straightforward. Again, we emphasize here the wide scope of applicability of our algorithm, since we do not assume any particular distribution of the random variables x1 to xn. The last application is the weighted sum of Poisson random variables whose PMF are given in equation 12. And the aim is to efficiently estimate the CDF of weighted sum of the random variable xi's, where wi are non-negative weights. In this case, we don't need to use the gamma process for the embedding. In fact, each xi has the same distribution at time t equal 1 as the continuous time Markov jump process, Poisson process xi of t, whose PDF is in 14. So in this case, it is sufficient to use the Poisson process to embed to construct the Markov process for in the embedding in the embedding step, right? Okay. A close look in the literature reveals that there is no Monte Carlo estimator that has been developed to estimate the probability or the CDF of weighted sum of Poisson random variables, and this means that constructing a competitor to the multi-level splitting to estimate the weighted sum of Poisson random variable will be of practical interest. This is the aim of this slide, where we use the concept of importance sampling to construct a second estimator of the CDF of weighted sum of Poisson random variable. First, we write the quantity of interest L as an expectation of the indicator function times L, the likelihood ratio, and the biased PDF or the importance sampling PDF is chosen to be as an equation 17, which is a Poisson random variable, or which is the PMF of Poisson random variable with a scaled rate. So this, instead of using lambda I to be the rate, we use lambda I times theta as the rate of the change, of the new variable. After this change of measure, the importance sampling estimator is given by equation 18, where each realization are sampled independently according to the biased PDF in equation 17. Regarding the choice of theta, we choose it to be such that, the expected value of the sum under the new measure is equal to gamma. And through a simple computation, we show that theta is given by equation 19. Now we'll talk briefly about two heuristics to choose the levels that will be used in the multi-level splitting. The first one is universally applicable, and the second one applies only to the sum of random variables. The criterion that we adopt to choose the levels is in equation 20. Let me here recall the definition of the decomposition of the probability of interest here, and the criterion to choose the intermediate level T1 to TL minus 1 is to make this conditional probability equal to a fixed P bar independent of time. So this is represented by equation 20. The first heuristic is based on running a pilot, which is represented by the green dots here, then interpolate to estimate the CDF, which is the blue curve here, and then use the inverse CDF, invert this curve in order to find the red points, which are the optimal approximate intermediate level that satisfies this equation 20. The second heuristic is based on lower bounding the quantity of interest, the probability of interest by this quantity, and then make the lower bound equal to P bar and find then T1, the time that solve this equation. Similarly, Ti is selected as the root of the nonlinear equation in 23. This second heuristic can be easily adjusted to the case of the sum of order statistics and to the weighted sum of Poisson random variables. And however, for a more complicated choice of S, the inverse complementary CDF heuristic, I mean the first heuristic, is preferable. Let's move now to the simulation results. In order to perform the comparison, we define the relative error, which is the coefficient of variation using M replications of an estimator L hat. This relative error is given in equation 24. It is up to a multiplicative constant equal to the relative half-width confidence interval resulting from the use of the center limit theorem. In order to include the computing time in our comparison, we define the work normalized relative variance metric, which is defined in 25 and is equal to the relative error squared times the computing time seconds. Note that when we compare to estimators, the one with the smaller work normalized relative variance is more efficient. Also, we would like to emphasize here that the work normalized relative variance is insensitive to changes in M. The first case is the weighted sum of Poisson random variable. We use the second level selection heuristic to determine the intermediate levels. The number of samples per level S is equal to 3000. And the algorithm is repeated 200 times in order to be able to estimate the mean and the variance by sample mean and sample variances. From this table, we clearly observe that the importance sampling estimator outperform the multi-level splitting. This observation does not exclude the multi-level splitting from being a very good approach, since it is still applicable to a wide range of of scenarios that will be presented later. The second example is the CDF of the partial sum of ordered random variable. We start with the Weibull distribution, and we compare our approach with that with the approach developed in this work. In this work, it was proven that when we consider the Weibull PDF, their importance sampling satisfied the bounded relative error, which is not satisfied by our estimator. And hence, we expect that in this particular case, when we consider the Weibull case, it is expected that the universal estimator to be more efficient than the multi-level splitting. However, when we consider the log normal case, we see clearly that the multi-level splitting outperforms the universal importance sampling estimator in this case. The last example is the CDF of the ratio of x1 and the sum from I equal 2 to n of xi plus eta, and the xi's are log normal in this case. We compare our approach to that in this paper, and in this case as well, the multi-level splitting outperforms the variance scaling importance sampling approach of this paper. To conclude, we proposed a dynamic multi-level splitting estimator to efficiently evaluate various time-independent wireless communication systems performances. The idea is to embed the static problem within a continuous time Markov process so that the distribution of interest corresponds to a snapshot of the Markov process at some time instant. We then apply a version of the classical multi-level splitting to construct our estimator. We showed that our estimator is featured with a wide scope of applicability, as illustrated in our examples of estimating various wireless performance metrics, and the numerical results showed that our estimator compares favorably with the existing estimators. Here are the references that I have used in this talk. And thank you for your attention.